If I use chemoselective conjugation and I circularly permute the proteins, the relative position of the various domains of the proteins relative to the sensing surface is changed, right? So in actual fact, I can tune proximity of these antigen binding domains of the single chain FB by permuting the molecule. Okay, so there is another mechanism by which you can use some protein engineering to specifically adjust distances, nanoscale distances within this device. Now, I won't cover this, but suffice it to say there's an opportunity also if you have a SAM on the surface to shorten up the SAM to make the SAM more ideal, and that also affects sensitivity. So I will skip over these points. These have to do with my ire with the existing conventional wisdom about the infeasibility of FET sensing at physiological salt, which isn't true, but I had a horrible time funding this work when I first did it. I basically had to do it first and then show that it worked before I could get funding, and that's extremely frustrating. But what I will tell you is that I think that the experiences that we've had here indicate that, in fact, you can tune the proteins for very specific function to address a nanoscale problem. In this case, the nanoscale problem is the critical distance between charges on analyte and the sensing surface. And I've shown you a couple of mechanisms by which you can adjust it. And so what that says to me is that hopefully within nanotechnology, there may be a role for persons like myself to play. And so I'm hoping that we molecular biologists actually can play a role with you guys. And so I took on this project as a way to demonstrate that we could address such a problem. And the folks involved in generating this were my graduate students, my collaborators in the Department of Electrical Engineering who made the Algan heterojunction structures, Wu Lu, Len Brilson, Zhujin Wen. And then we didn't cover this, but I also have collaborators in the OSU Department of Material Science who helped me characterize the SAM on the surface and the protein-SAM interfaces for thickness, robustness, and a number of other parameters. And of course, one always has to acknowledge who gives you the money to play with. And so in our case, it's National Science Foundation and Department of Homeland Security. So that's it. Thank you for your attention, and I'll take any questions you might have. Yes, sir.
Hi, I'm Tad Hogue.
Yes, yes.
So do you have kind of anything you can say about false positives and things? Are there other sorts of proteins around that might bind more weakly but have higher concentrations?
So that depends so there's two factors that determine whether or not that's a problem for you. One is, as you're well aware, MIG is a chemokine. It's part of a large family of related proteins. And so like I was emphasizing how important it is to select the correct epitope recognition specificity to get maximal sensitivity. It's also important because some of the epitopes are conserved from chemokine to chemokine, right? And so you can end up reading other proteins, okay? But what we can say, and what others who have been working with FET sensors can also say, is that there is a specific fingerprint, if you will, electrically of the polypeptides, because, you know, so two chemokines, even though they share an epitope in common, overall have different amino acid sequences. And you can pick apart which chemokine had to be on your sensor by shifting the pH and watching the response of the sensor as a function of the shifts in the pH. Yes, sir. Oh, it's surface chemist.
Jay Hickman, UCF. I think what your research is doing, simulation modeling are great tools, but I think you've shown is that the pratfalls of over-interpreting it sometimes and ruling out whole areas of interest. But very, very nice chemistry surface chemistry that you've
Thank
done.
you.
Did you actually do any of the measurements in serum or just even
So
in BSA solutions or anything else like that?
So mostly we've done them in a physiological buffer because so basically in PBS, but we're starting now to do them in serum. And the question I bet you're ready to ask is, am I getting other gunk onto our sensor?
Well, no, of course you are. But so the
Yes.
question is whether or not.
Well, thank you.
You know, no, you are. Just
Yeah,
50 years worth of.
it's unavoidable,
Yeah,
yes.
But the point is, what I'm curious about is whether or not the other proteins and everything are going to disrupt the very nice and elegant surface chemistry you've done, because sometimes they do hold up. That kind of chemistry does hold up in physiological situations. It'd be interesting to see whether or not yours does as well.
So I can't tell you for certain at this point. I'm expecting that, so there's a lot known about the oxime conjugation chemistry, and the oxime bond is, unlike some of the other chemoselective
Well, actually,
conjugation, is not very labile. So I expect it will.
I'm not worried about that aspect of it, because I mean, Carolyn Bertozzi has shown that you can actually
Yes.
decorate the outsides of cells with it and do chemistry in
Yes.
physiological systems. So that's fine. It's whether or not you can actually retain the orientation on the surface.
So one of the things I glossed over, and what you're sort of alluding to, is that these things have some conformational freedom, right? They're not rigid bodies.
Right.
Okay, and so by and large, so I have oriented them to some extent, but I expect that there are a variety of different possible conformations that this system adopts.
Well, because what's really interesting is when the other proteins absorb and in some cases denature, you get this reorganization
Yes.
effect. And I'm wondering whether that reorganization is going to involve your molecules or not, or whether or not you've got it stable enough.
I can't
because
tell
that'd be
you.
very interesting to find out, because then you would have something that would hold up under physiological
Right.
conditions.
So that's a significant issue. I can't tell you what the answer is right now.
Got a question from Dr. Borges is next, right behind you. Yeah, there.
Yes, sir.
Allow me. A little difference in height.
That was
Bob
interesting.
Borges from UAB. I just wanted to comment. I admire your persistence. You knew.
Oh, thank you.
You knew you were right. You were right, and you proved it. Great job.
Thank you. Thank you.
Okay, sorry, sir.
Again, it's really beautiful presentation. And I wonder about masking effect. Since you're dealing with charged molecules, you're always worried. I mean, you show a very nice problematic effect of the ions, but you have a
Yeah,
lot
yeah.
of, I'm not sure you aim really to get the effect in the serum at all. You may look for a local effect that may be a little bit cleaner, isn't it? Or what you're looking for?
Yeah, so in actual fact, I don't know how the sensor performs in serum. That's one of the things we intend to do next. But yeah, what you're suggesting is a potentially significant problem. I just don't know the answer yet.
Yes, please.
Yes, sir.
Yeah. Yeah, so this was beautiful, and this is, I guess, more of a comment than a question. I thought it was a little modest about the possibilities of using this sensor, because this interface, this antibody-antigen interface, is actually something that has undergone at least 400 million years of research and development before you started on it. It is designed to operate in the environment where you're operating it, in serum. And it seems like it has a tremendous potential for high specificity interactions under the conditions where you're looking for them.
I hope so. I can't say with certainty because I haven't done the sensing experiments in serum, but I hope so. Remember, these are also, the libraries I'm using are semi-synthetic. These are actually antibody fragments that, to some extent, are not precedented in your natural repertoire. So there may be some differences, right? So the CDRs are actually made by synthetic oligochemistry.
The CDRs are made that way, but the frameworks are natural.
Yes, absolutely correct.
And that's the way the immune
Absolutely
system
correct.
works, is that everything in your repertoire is, well, not everything in your repertoire is to some degree new and never tested before.
Yeah, so your repertoire.
I mean, I don't want to get in a big argument over this, but it's a nice system.
Yeah, your repertoire probably contains something like 10 to the 10 to 10 to the 11 different specificities, right? well, B cell repertoire is what I was.
Potentially much more.
Okay, well, okay, very good. Well then, all right, I'll take greater credit than Thank you for that.